In the video on classification with the Auto Model feature, we provided an introduction to the tool and its usage in conjunction with classification. In this tutorial, we want to introduce the other two options in which to use it, clustering and outlier detection. Together with classification, they're the main tasks solved with machine learning. For this demo, we will use again a dataset which is shipped with RapidMiner Studio. Of course, you can also load or import your own datasets. The dataset is called Sonar. Sonar stands for Sound, Navigation, and Ranging and is a technique used for hunting and orientation, for example, by bats and dolphins. Humans are using the sonar technology mostly underwater or for geo-exploration. The technology is as simple as emitting an acoustic signal and then interpreting the echo which is returned with respect to duration and characteristics. The data in the sonar example set are sonar returns collected from a metal cylinder and a cylindrically shaped rock positioned on a sandy ocean floor. We have a total of 208 return signals, out of which each is described with 60 different data points, representing the response amplitude of a certain frequency band. The original idea of the experiment was to identify the different objects via applying a neural network model for classification. The classification was then given as rock versus mine, originally called a metal cylinder. However, classification is not our task in this tutorial, but we want to find some clusters in our data. All attributes or columns are now checked if they're acceptable for our usage, and the result is indicated with a traffic light color. To understand the colors and the quality bars in more detail, please refer to the information panel and the auto model and classification video. As you can see here from a pure data quality and applicability perspective, the data of our label could also be used for clustering, but we will exclude it as it is not relevant for our clustering. Now we're presented with the option to configure the general overview and with the configurations for two different clustering algorithms. K-means clustering always requires the input of how many clusters are to be formed up front. We'll just check the results if we look, for example, for 3 different clusters in our data. Check out 5 Minutes with Ingo in our YouTube channel to get a great explanation on how K-means work. Of course, there's also some additional details in the information panel. X-means allows us to simply define an upper and lower limit for the number of clusters. The default is set from 2 to 20, which accommodates a large number of clusters, so we can keep that as well. So the first thing we can look at is the correlations. As you can see, there are close correlations between the attributes, for the obvious reason that they're adjacent frequency bands, and as such not independent. Further, you get a nice overview for the results of each clustering method. For K-means, we have clustered the data into 3 clusters. Cluster 0, Cluster 1, and Cluster 2. Cluster 0 contains 85 out of the 208 examples, which is a bit more than 40% of all examples. With an average distance of just a little under 30, Cluster 0 is much denser than the other two, especially Cluster 1 is relatively loose. The characteristics of the clusters are shown here. For example, Cluster 0 is prominently below average in these 3 attributes. The clusters 1 and 2 have both values significantly above average in 3 dominant attributes each. The same is apparent here again in the heat map, which shows all the 9 attributes mentioned before, with red indicating values above and green below average. You can also look at the clustering in the form of a decision tree. It is showing that clusters 0 and 2 were formed around these relatively clear paths, whereas cluster 1 basically consists of the remainders. For the rest, let's jump to the results of the X-means algorithm, which has identified 4 clusters. Here you can look at the centroid chart to see the average characteristics across all attributes. And of course, we also provide the data for those centroids. The scatter plot tab shows a 2-dimensional representation using the 2 most discriminatory attributes. Cluster 3, for example, has a strong characteristic in attributes 16 and 17, and you can see the points are nicely congregating around here. Last but not least, we show down here the main result of the clustering, which is the clustered data. Now, we use the same data to identify if we have any outliers. In our case, this might be, for example, cases with bad signal recording. We could then remove those upon identification and redo the clustering to get a potentially better result. Just for consistency, I'll uncheck again the class. We've discussed it before, so I'll turn off the correlations this time. With our small example set, we can increase the percentage here a bit to 2. And here you see the output for each of our 2 outlier detection methods as flags, and here even with the absolute values. You can now investigate the ones which are indicated. As mentioned also in the other auto model video, it is important to note that nothing here is done in a black box, but rather the opposite. So in case you want to edit the underlying process, you can do that just by opening it here. You have now all the different steps displayed and annotated nicely, so you can swiftly find your way around to check and change as you please. With this, we end this tutorial on clustering and outlier detection with the auto model feature. Thank you very much for watching.